All right, so let's keep on going with adding stuff to an alkene. Now we're going to look at halogenation. And halogenation is just the addition of a diatomic halogen across an alkene. And it's going to do this in an anti-fashion, meaning the two halogens will end up trans to each other. Now, most commonly, we'll use chlorine or bromine, sometimes iodine, but very, very rarely fluorine. So, but chlorine and bromine are the most common ones you're going to see. And so we're going to take a halogen. Again, remember halogens are one of our diatomic elements. And it will add to the alkene so that one bromine is going up and the other is going down. And it will lead, in this case, in this particular example, to a racemic mixture. Now, one important thing to note is you will never see a syn addition in this way. And so the mechanism has to be able to address why only the anti-products are observed. So let's take a look at the mechanism. So in the first step, one of the bromines is going to make a bond to one side of the double bond, and the pi electrons simultaneously make a bond to that same bromine. This is kind of like the oxymercuration step a few pages ago. And that bromine, because the alkene is flat, it's trigonal planar, that bromine can add upwards to make this three-membered ring. It does that 50% of the time. And the other 50% of the time, it adds downwards. Now, this is called a bromonium ion, or sometimes you might hear it referred to as a bromonium ion bridge. But like the oxymercuration reaction, it's a fairly um, ring-strained intermediate. And so will happen next is the bromine that we just kicked off over here is going to be a nucleophile as bromide and attack that ring. So I want you to think about this for a second. If you have that huge bromine going upwards, do you think this same bromine wants to come from above and attack? No, it wants to come from the path of least resistance. So it's going to come from below and open that ring up. And when it does that, one bromine is up and one bromine is down. The bromide will never attack from the same direction as that bromonium ion bridge. And so that's why you cannot get the syn addition. In contrast, when that bridge is going downwards, bromonium ion will attack, or I'm sorry, the bromide will attack from above, open up the ring, and that's how we get the enantiomer. And since it's exactly half and half, that's a racemic mixture. Now, kind of like I did on the previous page, I want to use a comparison between a cis and trans isomer of an alkene and see if there is any result or any different result in stereochemistry. All right, so I'm going to add bromine to this alkene. I know that one bromine should be going up and the other should be going down. And I'll get the opposite. I should get the enantiomer. But like I said, when I've added the same group to an alkene and there's this possibility of symmetry, I need to ask myself, are these symmetrical? So if I cut this down the middle like this, I might have the same groups, but they are not all going in the same direction. So there's no symmetry between these bromines here. So this really is the enantiomer. The second product is the enantiomer of the first product. And so we get a racemic mixture. Now, starting with the trans alkene, again, I'm going to um, add the bromine in an anti-fashion. Does that look like it's symmetrical? You might look at it very quickly and say, no, of course not. They're not going in the same directions. But what can you do with single bonds that aren't involved in a ring? I can rotate them around. If I rotate one of those carbons around or rotate that single bond, now this bromine up here, or the bromine that has to have the solid, I'm sorry, the dashed wedge, when I rotate it around, it's now coming out at you. What do you notice now? There's symmetry there. And so this ends up being a meso compound. If you had drawn this here and said, oh, it's a racemic mixture, you would lose points because this is the same exact thing as that. A meso compound cannot have an enantiomer. If you try to draw its enantiomer, it ends up being completely identical to it.